Okay, Gary, welcome to Montreal. This is a terrible welcome that you had. And I'm going to introduce you officially in French. Comment? I'm going to introduce you in French, and then I'm going to hand the controls over to Gary. Just a second now. Where am I gonna? I think it's here. No. Okay. This is. OK. Bon, alors, bienvenue à... OK, s'il vous plaît, maintenant, arrêtez de parler parce que on n'entend pas. Ben, ils s'en viennent pour ça. Ça c'est un autre problème. Bon, mais arrêtez de parler, s'il vous plaît, parce que c'est pris par l'enregistrement. Silence. Voilà. Alors, bienvenue. Je veux souhaiter bienvenue à Gary LUPYAN, qui va parler de l'efficacité déraisonnable de l'appariement de formes. Il est professeur de psychologie un instant à l'Université de Wisconsin et il est professeur affilié de philosophie aussi à Wisconsin-Madison. Ses recherches portent sur la manière dont le langage, la langue, façonne la cognition et la perception, sur l'évolution du langage et sur la façon dont les langues s'adaptent aux besoins de leurs usagers et leurs apprenants. Ces travaux récents visent à comprendre ce que les humains, les systèmes artificiels peuvent ou ne peuvent pas apprendre à partir du langage, ainsi que le rôle des entrées langagières naturelles dans la construction d'une intelligence de type humaine. Okay, now enough of this. Do you speak French at all, Gary?
No.
Okay, so enough of this mystery for you. I'm very happy to welcome you in Montreal, and I pass the whole ceremony over to you.
All right. Thank you, Seven, and it's good to be back in this talk series. It's always generates good discussion, and this time we're starting late, but my talk is not overwhelmingly long, so there should be plenty of time. The title of the talk, of course, makes reference to a famous paper by Gene Wigner, The Unreasonable Effectiveness of Mathematics, where he remarked on the miracle of the appropriateness of mathematics for sort of the formulation of the laws of physics, kind of this sentiment that it's a wonderful gift for which we neither understand nor deserve. And he compared it to the striking nature of the way the human mind can string together 1,000 arguments without getting itself into contradictions. Of course, it often does, but it does manage to maintain a coherent model quite well. And so this brings us to the question that that motivated the preprint, The Unreasonable Effectiveness of Pattern Matching, that sort of in a circuitous way led to this quite, I think, surprising and remarkable discovery about LLMs as pattern matching machines with, as I'll argue, relevance to human cognition. So what sort of intelligence can we think, do we think large language models are implementing? And if you've been following the dialectic over the last now 4 years or so, it's quite a range, and the variance continues to be high. So you have in the earlier days of ChatGPT, in that first year, you have articles like this from Jaron Lanier maintaining that there is no AI. This is just about information retrieval, right? And so just as we would not want to endow a database with intelligence. It's clearly about what the user thinks to retrieve, right? The database itself has no intelligence. So similarly, you can say, well, large language models, they're just a much more flexible version of that. And then, of course, there is the still, often repeated analogy between LLMs and imitation. So Emily Bender's stochastic parrots idea, right? The models are built on statistics. They work by looking for patterns, huge troves of text. And importantly for this argument, we are nothing like that. You are not a parrot. Okay. And a more sophisticated version of this argument comes up in thinking about reasoning, planning, thinking, and these things that we talk about people doing, and whatever it is the LLMs might be doing, right? So Melanie Mitchell, she poses this sort of question: are these models understanding and reasoning in a general way, or are they doing what AI researcher Sabara Kamabati calls approximate retrieval? Can you guys in the room hear? Should I pause? Okay. Stefan, can people hear in the room, or? You're muted.
So out here in cyberspace, we can hear you.
Okay.
Yeah.
So let's continue in cyberspace while they're trying to sort it out in local space.
Okay. So, Stefan, you can see the slides, but you can't hear? Or
now they hear everything.
You can't see this.
That's strange. I don't know why.
Okay.
Ok, entre-temps, est-ce qu'il peut continuer? Okay, continue.
Okay. Here's what he actually writes. Nothing I have read, verified, or done gives me any compelling reason to believe that LLMs do reasoning planning as it is normally understood. Okay. What they do is a form of universal approximate pattern, approximate retrieval. It can sometimes be mistaken for reasoning. Okay, and importantly, the argument here is that if you are doing this kind of approximate retrieval, pattern matching, you are not doing, hence the or, right? That is not real understanding or real reasoning. Some more examples. Model doesn't engage in structured logical reasoning the way humans do, the real thing. Okay, and the empirical demonstrations for this often take the following form. The models are tested on various tasks, and they are better at doing a version of the task that's more well represented in their training data, and they're worse at some counterfactual version of the task, leading people to make claims like this, that they rely on narrow, non-transferable procedures for task solving. So, for example, a paper from last year from Apple, The Illusion of Thinking. What supports this argument that it's just an illusion? Well, they're comparing here, systematically comparing reasoning models and non-reasoning LLMs. And they found that large reasoning models have limitations. They fail to use explicit algorithms, reason inconsistently across puzzles. For example, on the Tower of Hanoi puzzle, where you stack disks from one, you have to transfer disks from peg here 0 to 2, and the smaller disk has to be always above the larger disk. Okay, and so the large reasoning models outperform the non-reasoning models, but then after problem complexity increases, so the x-axis here is the number of disks, So, 1, 2, 3 disks, fine, and then 4, 5, 6, and it collapses. Okay, and if it were just running an algorithm, that this should not happen. The memory involved is, well within the capacity of what the model should be able to handle. So as complexity increases, reasoning models outperform, but require more tokens until both collapse. So I want to suggest that what all these critiques have in common is that they take a very particular view of human cognition, one that has old historical roots. So this is George Boole, okay? And his 1854 treatise that introduced Boolean algebra, what he was after was not mathematical framework, formalism. The name of his work was The Laws of Thought. So what he thought he was discovering was the laws of thought. And there is some great irony in this because, of course, this was one of the developments that made computers possible. An extraordinarily useful framework. But I'm going to argue one that is hardly the normative one for the way that we actually think. 180 years before him, Leibniz, of course, put forward a vision that at some future point we will understand the laws of thought well enough that you can just calculate, right? So just as accountants can put their differences aside by just seeing whose calculation is correct, so philosophers, scientists could just, calculate, just follow the logic. And so there is, we need to admit, right, this type of definition of reasoning, of sound reasoning, right, that is extraordinarily useful, that there is a reason why computers are as useful as they are. They can implement sound reasoning. And so in this really fun paper, from the earlier era of LLMs, this was released shortly after GPT-4 was released. So Arcutis argued that, there are many domains where there's no such thing as good enough. So 4 tires on a car might be a 75% success rate, but that's not good enough. So computation-heavy, reasoning-heavy applications are not like recommendation engines. They need to be sound. The problem is that typical human reasoning, typical thinking is not especially sound. Okay, so if we look at human performance on tasks like this, it's far worse than what LLMs do, right? So here is Tower of Hanoi data, just from 2-disk and 3-disk versions. The x-axis shows age. So groups of 6-year-olds, 7-year-olds, and so on up to college students. And, starting at age 8, kids can do the 2-disk version. Even 8-year-olds can do the 2-disk version. Even the 3-disk version poses substantial difficulties for adults. Never mind the 4 or 5-disk version. This is difficult. There's a lot of classic work in cognitive psychology on these kinds of reasoning problems. Here's a paper from Katofsky, Hayes, and Herbert Simon, where they gave people lots of variants of Tower of Hanoi problems, isomorphic variants where the algorithm is exactly the same, and yet some versions they found to be up to 16 times more difficult than other versions. So there are just literally hundreds of papers of this sort demonstrating that what humans are doing is not sound reasoning. What humans are doing is not thinking on this definition of thinking, the thinking or approximate retrieval. Here is just one example from our data. This is part of a larger study. So if you give people syllogisms like this, okay, Pittsburgh is in Pennsylvania. Pennsylvania is in the United States. Therefore, Pittsburgh is in the United States. They have to judge the validity of the argument. Okay, good. Yeah, valid. Here's another one that's valid. Okay. That's much more difficult, right? It conflicts with people's prior knowledge. Here's one that doesn't conflict with prior knowledge because it just uses nonsense words, but has the same form. And that is also relatively difficult. It doesn't take much to get people to basically chance level on this. Interestingly, these kinds of content effects in syllogistic reasoning are also found in large language models, at least the smaller ones. The bigger ones just perform at ceiling on these kinds of relatively easy tasks. But here I'm showing you the human data. So consistent with prior knowledge is in blue. Inconsistent, violates prior knowledge is in purple. In the middle is just nonsense. Okay, valid, invalid. Again, here are various models, and already at GPT-4, they're starting to perform at ceiling. This is fine-tuned, but what they sort of do out of the box is to show a human-like pattern of errors, not exactly, but roughly consistent with it. That's that paper. Okay, and here too, of course, if we look at what kind of counterfactual tasks people, the models are performing more poorly at, we can raise what I think is a reasonable point that for people too, right, base 10 arithmetic is much easier than base 9. Not because it's inherently easier, but because they've had lots of practice with it, and the practice goes a long way. People are bad enough with normal compass directions. Okay, if you flip it around, cause them to where north is not up but it's to the left or toward the bottom, they too have a harder time with it. And this is drawing something rotated 180 degrees, and the image models have a harder time with the rotations. Well, it's also harder for people to just draw something upside down. Okay, the way that people would solve that task is to draw it in a normal way and then flip it upside down, right? So people show these kinds of generalization failures. This is just the normal part of biological cognition. There are generalization costs, even to fairly narrow generalization. So the argument is that, yes, LLMs are not sound reasoners, neither are people, both are pattern machines. But pattern matching, rather than being limited to these shallow, narrow kind of generalizations, just kind of retrieval from memory, but in a more flexible, blurrier way, I'm going to argue is unreasonably effective. And it's not an alternative to real thinking, but it's the key ingredient. And so I'm going to make the argument with two characters, the Jabberwocky and the Gostak. We didn't intend it this way. It just kind of came out that way, that the way to show the unreasonable effectiveness of patterns, the way we chose to show it, was to rely on this ability that people, and as we'll see, LLMs, have to use pattern matching abilities to make sense of apparent nonsense. So Jabberwocky is, of course, comes from Lewis Carroll's Alice Through the Looking Glass. I think it's really, I tried to find whether this was the first nonsense poem of this sort, and I think it does seem that way. So there are many reasons why people can make sense of this poem. One, of course, is that a lot of the words are just regular English words. It uses English syntax, morphology, and a lot of the quote-unquote nonsense words are portmanteaus. And actually, Lewis Carroll himself coined that term, portmanteau, after the suitcase to refer to words that combine two meanings. People delight in translating the poems. It's been translated, I think, over 100 languages. And the challenge, the translation challenge here, is to convey the same kind of meaning and from nonsense, which in Chinese requires creating novel characters, which is kind of cool. So Josh, do you have a question?
Yeah, I ask, maybe you're going to get to this. How would you characterize, if there is a difference, the difference between pattern matching of word sequences versus pattern matching of, for lack of a better word, like Platonic concepts? And is there any difference, or is this just sort of quibbling over representations?
Let me circle back to that question after I go through the data. I'm not sure what evidence there is for Platonic concepts. And so, I mean, there's obviously abstraction, generalization, but I think these patterns at work are not quite, they wouldn't meet the definition of Platonic concepts, but they're also not just sequences of words. Yeah. Okay, so thanks for the question. So that's the Jabberwocky. The GOSTAC comes from an essay by this little-known Massachusetts schoolmaster, Andrew Ingraham, in the 1880s. He became the schoolmaster of this school, the Swain Free School, Massachusetts. And he published this book. This is from 1903. It's a very quirky, fun book. You can find it online. One of the chapters is 9 uses of language. And in this chapter, he talks about, there's a section where he talks about one of the uses is using language for thinking. And he notes on this remarkable ability people have. He also notes kind of, this is way before distributional semantics. He talks about words hanging together as things with things, that there's a parallelism between the two. It's a very astute observation. So here, I suppose someone were to assert the GOSTAC distims the dashes, even though you don't know what a GOSTAC is, what distimming is, what the dashes are, there is a lot that you can infer from this statement. Various kinds of inferences you can draw, both linguistic, right? The dashes are things that can be counted, okay? The distimming is an action that can be performed on dashes, right? But also these more logical inferences, okay? Now, this idea came to be studied first by Roger Brown in the 50s with first experiments on syntactic bootstrapping, how kids, he tested 5 to 7-year-olds, depending on the context in which a novel word occurred, they quickly made inferences about, is this an action? Is this a count noun? Is this a mass noun? And then there was a whole literature on learning words from context, from structural cues in context, generally in very simple paradigms. A fun side point here is that the GOSTAC, so it came to have this life as a linguistic example. And in 2001, this guy created an interactive fiction game called the GOSTAC that's based on this idea of people being able to figure out meaning from this kind of Gostakian language. And so if you're familiar with these text-based interactive fiction games, it works just like a normal game, right? You're plunged into this world, you can perform various actions. In a normal interactive fiction game, the actions are like, go north, open the door, inspect the book, pick up the key, right? Here it's the same, except that only the syntax and morphology are in English and some stop words there. all the content words are in Gustakian. And so, here's what let's see if this works. There we go. And you just have to figure it out. And if you put in an illegal command, it will tell you that that's not allowed. Oh, okay. So people can do this. It's not easy. They can play this game. 4 out of 5 stars. So can LLMs. So this was one of our early, very informal experiments. So what happens if you get an LLM to play the game? It doesn't do especially well. Neither do people, unless they're really dedicated. And in normal interactive fiction games, people will often draw a map to help them remember where everything is. Here, instead of a map, people create a dictionary. Okay. What's neat is after about 100 of these turns, so just a few minutes of play, you can. So the situation thought command is a template the LLM is using to think about the situation, cogitate on it, and then issue a command, and then the game engine returns a response. Okay, so the LLM is playing the role of a human in this game. And after a few minutes of gameplay, you can ask it to define the various words. We haven't formally tested how this compares to people's definitions, but the different models will converge on more or less the same meanings. And this is not because they're floating around on the internet. If you do this without, you can't let the model access the internet because it will find this information. But without internet access, it cannot define these words in any sensible way unless it plays the game. Okay. Now, it doesn't stop there, right? So this is the heart of this surprising and unreasonable effectiveness of pattern matching. We wanted to see what happens if you just give the model, without this interactive back and forth where you have lots of examples of words being used in various contexts and can converge on the meaning. What happens if you just give the model this kind of Jabberwockified text? It obviously detects that it has English syntax. We prompt it, say, this is, in this text, content words have been replaced with nonsense words. And I want to be very clear, these nonsense words are random. They don't match the number of letters. There's no frequency matching. It's reproducible. You can provide the same random number seed, but they're meant to be pronounceable because we're also doing this with people, but there is no algorithm to reverse engineer, right? It's just random word substitution. So we do part of speech tagging to make sure that inflectional suffixes are left and reattached. So let's see if there we go. Woped is some past tense. So that information is there, glorked, at least in this version. But that's it. Any similarity to existing English words will only be harmful. It will only mislead. Okay. And so when you ask the model to translate this back to conventional English, it translates it. How good is it? Well, here's the original. Okay, this happened to be the first example. It doesn't always work this well, but it also doesn't. This is not cherry picked, and I'll show you a lot more data. Okay, and so we next wanted to test this at scale, and so we use this. It's a really kind of interesting paper, but it's a really useful corpus for various reasons. But so we took 3 text genres: fiction, screenplays, and spoken language. These are podcast transcripts from this corpus. Let me show you some examples. These are about 400-word excerpts, slightly less, 300 word or so. So here is a transcript, podcast transcript. The podcast transcripts are a mess, lots of multi-speaker back and forth, lots of sentence fragments, okay? Here's fiction. Here's a screenplay from somewhere. Okay, and so there are 150 in each genre. How well? So we Jabberwockify it. We have the model translate it back. To put it in perspective, I'll show you some more examples. Anything above 0.6 is pretty good. And anything really above 0.8 is pretty much exactly, you know, it matches very well. Now we have, it's hard to compute random baselines here. One thing we did as a very conservative kind of baseline is we see, and I should mention, the way we calculate this is we take the OpenAI text embedding of the original text, of the translated text, and we see how similar those passage-wide embeddings are. And so one thing we can do is we can also see how much more similar is the translation to the original than to some other random passage in the same genre. And this is important to look at because if the translation is highly generic, it might be similar to the original, but it might also be similar to lots of other podcast transcripts. And here's the distribution of the baseline distributions. It's obviously a very reliable effect. There are a few cases where you do get generic translations, especially for the spoken excerpts, where it's similarly similar to some of the other transcripts. Okay, so it's kind of just generic. But in pretty much every other case, there's a substantial movement up. Which models can do this? We tested a range of models. The only model that was at chance was the 27 billion parameter Gemma base model. Interestingly, the same model, same training, just tuned, performs quite a bit better. But it's really the reasoning models. O3 Pro, I don't know why. We paid a lot of money to run this test. It did not perform especially well. But yeah, O3 medium reasoning effort, GPT-5, very similar. And we only tested Gemini 3 at the end, and that takes the lead. But these models are relatively similar, and they correlate at around 0.7 or so at the passage level. So the passages that are easiest to translate by one model tend to be passages that are easiest to translate by other models. The results I'll show you all come from this run from GPT-5. This is a 5.1 medium effort. So what kind of texts are easiest to translate? Well, here's a text that was translated word for word correct. Okay, exactly right. And what is it? Here is the original text. And here is the translation. Okay, and here it's pretty easy to figure out. You know, it's provenance. So this is Great Expectations. And so here, not only is this text present in the model's pre-training, it's very well represented. Okay, there are many, many versions of Great Expectations that has been sucked up by the model during its training. Okay, and so this raises the question of, well, does that matter? This is really interesting and impressive. And note that even if it were limited, if the model could only do this for texts that it's seen in pre-training, the abstraction involved from going from these nonsense strings using tokens the model has never seen before to the original text. That's already highly non-trivial. But that's not where it ends. So here's an example of a text excerpt from ESPN News. You can test the model the day the news comes out. So this precise news story is not accessible by the model. It's not present in pre-training. Here's the Jabberwockified version. Okay, and here's the translation. And Gemini actually is often will do this convenient thing where it will, when it, for the specific name, there is no way to recover that information. And so it will put in a placeholder. Okay, other times it will just guess a name. Okay. So not only does it figure out that this is about sports, new sports, but it's football, right? $12 million. Okay. Okay, and just, so if we plot the similarities, this level of translation, this level of accuracy, which, some details are missing, some of the meaning is distorted for sure, but of all the possible things this could be, this is pretty good. This is kind of right at the modal translation value across all of those 450 passages. Okay, so we can test the role of pre-training more systematically. So here are some texts that are guaranteed to not be in the pre-training. They're student essays, unpublished essays that undergrads have written and let us use. And then we took a version of the text that was about the same thing, but that was, in most of these cases, very much obviously in pre-training from Wikipedia. I'll give you an example in a moment. And so the mean translation accuracy is a bit higher for the online version compared to the offline, but there is no consistency here. Okay, you will notice that the few passages over here in the upper right that were translated word for word are all from online samples. So you're not going to recover something word for word, it seems, unless it's been in the pre-training. But there are many other cases, and I'll show you this one, where this is pretty good. This is over 0.9 cosine similarity in embeddings, and its Wikipedia version is quite bad. Okay, so here's this example. So here is the unpublished student essay. It's about a memoir, Testament of Youth, how World War I affected gender politics. And here's the Wikipedia entry on Testament of Youth. So we Jabberwockify both, translate them. And there's the translation from the Jabberwockified version. On the left, here's the translation of the Wikipedia article. It's this 0.5 is really an overestimate in this case. It's kind of garbage. It does get World War I, but it's pretty far from the original. Okay, whereas this one, so here's an example of the original first sentence and the translated first sentence. Okay, so pretty close. We've done some more systematic tests of what factors contribute to good meaning recovery. So the standard Jabberwocky condition is what I've shown you. We can also remove more information. So the standard condition retains the standard stop word list. So some modal verbs, prepositions, pronouns, articles. We can do things like remove all modal verbs, remove all verbs and prepositions, lowercase everything and remove numbers, okay, remove punctuation. And all of these things have effects. Okay. We have a lot more that we want to do with this, more selective surgery to look at what kinds of structural cues are especially helping. The blanks condition is an interesting one. Here's an example on this supremacy clause passage. So blanks, we just replace all content words with the word blank. So any intra-passage information that you get from a word being used several times in different contexts is now gone because all of it is just blank. You still get the blanked and blanks. Okay. Can still do it. In this case, it's even better. And if we look across the 450 passages, the mean of the blanks condition is actually exactly the same, even slightly higher than the standard one. The variance is also much larger. So what seems to be happening is that for some passages, and not surprisingly, it's ones that have more word repetitions, replacing all words with just the string blank hurts performance. But there are other passages where the model sort of can't help but use the form of the nonsense words in its recovery process, even though the form is irrelevant. And so the forms mislead. They're meant to not be similar to existing English words, but there's always some residual similarity. You can't avoid it. And so in those cases, removing the forms and just having basically a placeholder for all the words actually helps. And so some of those passages become easier to translate. We can also look at how this recoverability, this translation ability, changes across time. So we give the model just the first sentence, just the first 2 sentences, 3 sentences, and look at how well it can do it. And not surprisingly, there's always, this is just for 10 passages, I think, there's always a more context helps. So even though there's more complexity there, more context means more constraints. And so even for this great expectations passage that the model is able to match 100% of the time, if you just give it the first sentence, it can't. So that's the translation of the first sentence. It's nonsense. It's still a lot of nonsense. Here, it's getting better, and then here, it gets it exactly like the original. And so the first sentence is just insufficient. First 2, it's getting there. 3 sentences for this passage are good enough. Just to give you some more intuition, this is my last example, of the kind of patterns that are being used by the model. I want to show you another passage that we tested. This was in the preprint. This was also not in the pre-training. It was taken from a subreddit, the Netherlands subreddit, and the model was tested like the day that the post went up. It doesn't have access to it. Here's the post. This person wants to know if Unbeit-Speck, translated as breakfast bacon, can you eat it raw or do you need to cook it? So is it more like prosciutto, more like bacon? They've been researching in both English and Dutch, can't seem to find a consistent answer. Okay. If we look at the translation of the Jabberwockified version of this, you see something interesting. There's this very strong semantic fingerprint. It's about food. It's about how, whether something is safe to eat, not being familiar with it, researching. Okay, so the model can recover all of that, but the actual details about what the food is are different. So here is one thing we can do. We can take one word, Netherlands, and plug it back in. So instead of in the SPLUD, let's make it in the Netherlands. So now you're giving the model this extra constraint to try to interpret this nonsense in the context of the Netherlands. And what happens then is, and this is also, we tested different models, the models really start to converge here, is that it starts to get it pretty much exactly right. Okay, so here's an example from Gemini 3. Here's that same model that did the MSG version 03. So now, really the only difference is that the one on the right is about beef, the one on the left is about pork. You can see high level of details that are being accuracy matching in the details. And that one word is enough to move the overall similarity of the passage from as you can see, this measure is not great, but relatively it's okay. But it moves it from like 0.4 something to 0.8 something. So does this have anything to do with human cognition? This is the actual performance of the models is clearly superhuman. I like to argue that it's a difference in degree rather than difference in kind. People are doing this exact same type of thing. And this comes from classic connectionism. So the idea of thinking about cognition as constraint satisfaction. So if you have something like a Necker cube, it has some certain constraints in how it can be viewed. And those constraints, what makes it a Necker cube is that it has two solutions. And so as a result, two kind of equally good solutions, it will vacillate between two interpretations. And this was one of the early examples. So this is from Rumelhart 1989 chapter, the actual work is from the class PDP volumes. The idea that once you learn these constraints, in that early models, they were hand engineered, but now these constraints are all learnable. You just let the system run and it settles into a low energy state. It relaxes into a solution. And so Rumelhart writes about a large class of connections models containing constraint satisfaction that settle on locally optimal solutions through the process of relaxation. And so the argument we make in the preprint is that this is all there is. There's patterns all the way down, patterns all the way up. We're not the first to argue for this. So this book also from 1989 by Howard Margolis is a theory of human, high-level human cognition as pattern matching all the way down. The patterns are different, right? So neither Margolis nor we are saying that recognizing a familiar object and proving a mathematical theorem are the same process. We're also saying this is not a system one, system two qualitative difference. The patterns involved are different. Margolis has a kind of schematic of a spiral, right? So there are lower level tasks, higher level tasks, but it's not that one is sound reasoning and one is just pattern matching. And none of this is unique to language or syntax, right? So this operates in argue every domain. So here is, I don't know how this will come across to people viewing in very different conditions. Here's a blurred word that is meant to be fairly hard to read, but when placed in equally blurry context, so you're adding more constraints, but the constraints themselves would seem to, just like Jabberwocky, to not be very constraining. They're not very meaningful, and yet they help. So the king was married to the queen. There's a nice auditory version of this as well, where individually the words are nonsensical, but placed in a more constraining context. Now you can suddenly hear it. And so this idea of language processing as a system of constraints is most direct, sort of the theory of language that is most consistent with it are forms of construction grammars, where instead of viewing language processing as, you've got your grammar, which are content insensitive rules, and you've got your vocabulary, construction grammars merge the two. And so you have different, so patterns at different levels of abstraction. And clearly, what the models are doing here can't be done by just matching strings. And similarly, construction grammar, right? And so you have a pattern, the X or the Y, right? Which can be filled in with different kinds of content words. And so one way to think about what's happening with the LLMs is that they have learned an extremely powerful kind of meta-construction grammar representation of language. Okay, now, so far, people have tested, so how sensitive are people to this? And they are, but no one has seemingly thought that this could scale up in this way. So in this study, for example, Johnson and Goldberg, they wanted to see whether the sort of Jabberwocky sentences, what kind of real words do they prime? So if you hear he lorped it on the mope, you can test what English vocabulary words were activated by this. And you find that put is primed more than placed, and a word that doesn't fit into the construction grammar, like decorated, isn't activated at all. Okay. And so, it would seem like, well, yeah, he put it on the mope, that fits. He placed it on the mope. Well, turns out that statistically placed is less likely to occur in this kind of construction, but it still fits. And then decorated doesn't fit, right? But how do you know if it's, put, right, or laid, or like there are hundreds of verbs that would fit. Right? Well, if you give people more constraints, there was nowhere else to leave the car, so if you lorped it on the mope, that constrains it, right? And if you're thinking that, like, oh, I guess within this context, lorped might be park and mope might be a curb or median or something, well, so does an LLM. Okay, and we can keep going, right? So we can make the context itself less and less sensible, but it still retains, and this is what's so remarkable to me, it still retains enough constraints and enough signatures to allow a system to recover the information. Okay, so just to put everything back together, I want to call into question this assumption that real thinking, real reasoning, planning is somehow abstract, content-independent, logical. This is an old idea. You see it in Leibniz, you see it in Boole, and we now know that we know better, basically. We have been studying how humans reason, how humans plan and think, and it's extraordinarily hard to find cases of truly abstract, content-independent processes. And when those are required, people struggle. And this is precisely why we invented computers. Okay. And LLMs are not sound reasoners in some of the same ways that people are not sound reasoners. And this is, of course, a problem if you expect them to be. It's not a problem for me, who's most excited about them as models of human cognition. At the same time, the limits of pattern matching are far greater than I think what they might appear, and that both pattern matching and mathematics are unreasonably effective. Here's that preprint. It's linked in the email, and thank you. leave this up. All right, and Stephen, do you want to take questions?
You're still muted.
Fluge that we use to, okay, can you hear me now?
Yeah.
Okay. The ordering that I see over here, I see 3 hands. Can we just take it from Eddie, Paul, and Christoph? I don't know what happened to Felix.
Thank you. Thank you so much, Gary, for this wonderful talk and this very nice paper with Blaze. I enjoy reading this too. In the end of the paper and the end of the talk, you mentioned that there's something about us. Human cognition is pattern matching all the way down, just like LLMs in a sophisticated way. And there's also part of us that overcame these difficulties, that we can do math, science, and so on. So just say more about how we overcame this with the tools of writing, the tools of language, the tools of maybe communication with each other, and publication of the books and so on. But then what is the thing, the patterns, the more sophisticated patterns that we use to prove theorems and discover laws and so on?
Yeah. Well, precisely, and I think of it in the same way that sounds like you think of it, where we augment our cognition with all kinds of tools, language being first and foremost, but natural language is not good enough for math in most cases, and so we invent mathematical notation, and mathematical notation is also, it helps in just thinking about the math, but it allows us to externalize it, to write it down. And then, of course, paper is good, but being able to then have computing machines and calculators and computers that augment that further, right, helps to overcome our pattern matching limitations even more. And then there are also, and lots of people have written about this, but there's less work, and I think it's just harder to know even where to start. The sort of habits of thought and procedures, right? And so Margolis writes about this in that book, about that proving a theorem, like there are rules that you follow. You learn that certain kinds of next moves are legal and others are illegal. Same thing with games like chess, right? There are formal rules that you have to abide by. We can learn them, but that doesn't help you actually know what is the next reasonable move. It helps you rule out certain moves as just not in the running. But how do you know when proving a theorem, like what the next step should be? And there he argues that it's pattern matching. And so you're still reliant, but you're augmenting this process with, and so what's interesting is, the large reasoning models, they're not better at everything, but the kind of tasks that they're better at are those tasks that require more iteration, sort of going through and checking again, right? And this is also what we do when we want to make sure that we just didn't, do a kind of more superficial match. And
we have memory to help us in a way that we can check our past patterns and so on.
Yeah, exactly. And so I think the answer isn't in some special representational format, a kind of system 1, system 2 thing, or a special process, but in these habits of thought and a lot of cognitive tools. And so, you want your LLM to do sound logical reasoning, right? Plug it into a formal, right, logical system, right? That the limitation of these systems is that they don't know what to do. But once they're programmed, right, like they carry out the steps in a much more faster and more accurate way than we ever could. And also that, the LLM could, right? So yes, LLMs with their billions of parameters struggle with basic arithmetic, but they're pretty good in many cases at knowing which operations to carry out. So call up a calculator, because that's what we do.
So just to clarify, this is not a confirmation of this neurosymbolic approach, a combination of the two, like Gary Marcus would say. This is something like pattern matching all the way down. I mean, what is the difference here again about emergent symbols versus fundamental kind of combination of the two?
Well, so I think there's fascinating work happening in the mechanistic interpretability literature, and folks like Ellie Pavlik's work in particular in her lab, looking at, okay, as they scale, LLMs are figuring out there is such a thing as emergent symbols and compositionality. What's interesting is that what this work is revealing is that it's all sort of quasi-compositional, quasi-regular, quasi-symbolic, where the content is never discarded. It's not just that you figured out this is the right operation and it doesn't matter, right? This is how you do addition. Doesn't matter what the addends are. That's for the calculator. It doesn't matter as long as it fits in memory, right? It will do it. The LLMs are not like that. They're still, it's like, oh, okay, 7 + 8, I have that list, right? I don't need to run any more computations. And people are the same, right? This useful fact you've memorized, bring it to bear on the problem. Yeah, so my understanding of like the neurosymbolic take is that, yes, okay, there's connectionism for certain kinds of problems, but then you have this other, it's not about using writing or using a calculator. It's about pure symbol manipulation, right, in the brain. And it people can do algebra in their heads, right? You can do all kinds of symbolic operations, but it's limited, it's hard, and it's also very content dependent. Like the similarity to previous things you've practiced is always going to play a role.
Okay, Gary, 1 second. Just a procedural question. It's a constraint satisfaction problem. Do you want to have more questions and shorter answers from you, or do you want to give very
I'd like as many people as possible to have a voice, so I will be.
Okay, in return, what I'm going to do, which is illegal, I'm going to let this run beyond the time limit of the conference. What might happen is that it won't all get registered onto the video. But if there are people that haven't had a chance to ask things yet, I'm going to give it to you. It's now, I'm going to also alternate with local and distal. We have a local question here, and then we'll go to Paul.
Okay.
Thank you for your presentation. It was really interesting.
Wait, first ask if you're being heard. Can you hear?
It's very faint.
Very
Yeah,
faint.
it's faint.
Can you come up here? Yeah, just speak near this.
Hi, do you hear me better?
Yeah.
Okay, thank you for your presentation. It was really interesting. I have a question regarding the way reality is represented in this kind of tone. So if we figure out that it's embedded in, it comes from learned linguistic regularities, does it have to do with the perception of the world, of the person, or is it the real world? I mean, when we say we need to represent the world models, in what way do you think it's enough the way we figure it out? I don't know if it's clear.
So if I understood correctly, so is training on language enough? Is that
to represent the world model with enough pluralist? I mean, not the perception of only a person or two people who interact with the system.
I mean, I think one of the reasons LLMs require as much training as they do is that trying to learn all this from language is extraordinarily difficult, and certain kinds of things are just unlearnable or just very inefficient. So obviously, I don't think that people are learning all of this from natural language. To me, it's surprising how much can be learned from natural language. But to be able to predict natural language, I mean, lots of people have made the same point. You can't just learn, you can't get good at predicting the next word without learning much more general world knowledge. And in particular, what the models seem to be, really excel at is learning pragmatics, learning speaker intent. They are extraordinarily good at, from taking your vague, ambiguous prompt and interpreting it in reasonable ways. It's really quite shocking. On the other hand, even the best models, are pretty lousy at spatial cognition, right? So like learning about space and spatial configuration relationships from language is really hard. And training them on still images is also, doesn't do much. And, I'd expect that if they were embodied in the real world and being made to make decisions about, where to go and what to do, right? That's just a much more data efficient way of learning, at least that aspect of a world model.
Thank you. So if I understand well, the come is not done yet. So in this case, where do you figure out the system now? Nowadays, systems to fail in kind of different languages, new dialects, not knowing enough about reality. Do you think about this side of, okay, it works until when?
I'm sorry, I didn't hear part of it.
Okay, we're gonna have to cut that off, because for people here, if you want to be heard, be prepared to come up to my computer and say it there. Paul.
Thank you very much. Wonderful talk, Gary. I'm going to say 5 things, and you're allowed to pick one of them to respond to. The first is, as my hearing is failing, I understand now why I have such interesting conversations. The second is, your work uses language and is about language, which is one of, I would claim, several facets of intelligence. The third question would be, do you think the LLMs are ready yet to be able to invent notations, if that were the need? The fourth is, the squirrel in my backyard who gets into the bird feeder is clearly thinking a lot, and I don't believe he has language at all. And the fifth will be the one I sent you in the email yesterday from the Abbott and Costello routine, where Costello winds up saying, I throw it to who? And when Abbott says, that's right, he says, I don't even know what I'm talking about. Do you believe that the LLM knows what it's talking about? Pick anyone.
I think, just briefly on the last point, I mean, I don't know what, believe what one is talking about really means if you if you ask a person, do you really know what you're talking about, right? What exactly, at what point do you say yes and maybe and no? But clearly the intentionality and agency of people in LLMs are very different. Our goals are different. And it's, I think LLMs are good model organisms of various kinds of cognitive processes. I would never want to say that they are, good models of people in their entirety. So yes, there are different ways of thinking. I think there isn't a sharp division between like doing language and doing other things. It's all much more integrated. But let me just say a few words about the squirrels. I think you're right. I think other animals certainly think. They don't have language, and I think that in part because we have language, I think and these these normative systems for reasoning, there is a tendency to over idealize human cognition as being this rule following or highly explicit thing, because often we do have explicit goals. If you ask someone, what are you trying to do? They can often tell you, and sometimes you can show that they're just confabulating, they're wrong, but most of the time, the explanations are reasonable. But it doesn't mean that those actions were caused in some very rigorous way. They didn't stem from those explicit reasons. And so I think we do have this tendency, to over-formalize human cognition, when in fact, in many respects, it has much more parallels to cognition in other animals. But add language, add a few other things, and you get, So
Thanks very much.
Okay, we'll move to the next question, Christoph, and let me say to the group here, tell me if you have a question that you want to ask, because we'll put you into the queue. Christoph, welcome back. Go ahead. You turn on your mic. Turn on your mic. We cannot hear you, Christoph. Turn on your mic.
Okay, now you can hear me?
Yes.
First mic, but for some reason the other one doesn't work. So yeah, thanks for the great talk. I'm happy to be here. Usually I have a seminar at the same time, so I can't be here. But I think this is really a great talk. I think Gary is really up to something with regard to the patterns and their importance for human reasoning. Now, what I wonder, however, is this really the same kind of reasoning we have in humans and large language models, or is there maybe an intermediate step, so to say, which is kind of missing in this account? Many people say, well, because large language models and humans show similar phenomena, they seem to be very similar, and so they have the same workings. But what large language models, in my view, do is they work with text, obviously, or maybe other things, but let's talk about text as Gary did today. So there is something, of course, there's something unreasonably effective about large language models, because it's kind of surprising that there can be so much done just with language processing. But there's also something to be expected, that a lot of thinking expresses in language, and that language is able to capture in patterns, because language is patterns through and through. There are patterns, sometimes structures, but language just needs to work with patterns. These patterns reflect some of the thinking, but it's only some of the thinking of what humans are doing. There's much more. So like the squirrel, it's doing something without this external device of extended language, symbolic language. And still it has a lot of similarities with humans. It has a lot of cognitive abilities that are comparable to humans. So maybe there's something like a step in between. We do these patterned technology of writing, and this technology reflects some of our thinking, but it's not that these models directly model human thinking. You see what I'm getting to?
Yeah. So I mean, it's clear to me that were it not for all of this written text, we would not have technology like large language models, because training them on other things gets them good at those other things, but they are fairly narrow. I think that it's not coincidental that training on language is especially powerful, because language is this categorical system of abstractions that are useful, that we through cultural evolution have come up with, because these are useful things for us to communicate about and to contrast. And so the models are sort of reverse engineering the human world from our language use. I would argue that to some extent, to a large extent, people are benefiting from language created by others in a lot of the same way. We are learning lots and lots of things through language, things that we could in most cases, but would not learn in its absence. So the kind of alinguistic human cognition, human cognition without the benefit of language, it's certainly an intelligence, but it's quite different from human intelligence with the benefit of language. My normal research program focuses more squarely on that question, but I think this the deeper point here about patterns is, in this case, it's because of language. But I'm thinking of, for example, Justin Wood's work, where they're looking at development in chicks and little chick transformer models that are trained on the same visual input, and you have the development in the transformers of a lot of the same supposedly, core knowledge sorts of mechanisms that were argued to be unlearnable from data, and clearly they are learnable. And in that case, what the transformers are predicting is not language, but just what comes next. So just the visual input and trying to lower prediction error. And from that, you get sort of object concepts, you get imprinting, you get all kinds of abstractions that are not directly in the input, but emerge from trying to predict it. And of course, predicting language allows you to learn much more. And so it's not, I think, that the models are. So I also recommend people look at, so Anthropic has this, came out last year, I think, Biology of a Language Model, where they, and it's interactive, you can play around with it, this really nice interpretability work, where they try to figure out through case studies, right, what is the model representing when it does something. And you have, it's not about single words, it's about these more general nodes. And to Josh's earlier point, when you look at that, you don't think Platonic concepts. It's still very context dependent, but it's also not about like a specific word. You have emergent categories of, certain kinds of actions, language, like that this is Japanese, right? Kind of regardless of what's being said, but some Japanese inputs will activate it more than others. Or, a sports node, like this is about sports, right? It's not dependent on the word sport.
Okay, we're now going into overtime, which is fine. And I just have to say two things. Christian, Douglas, Eddie, stay there. You're going to get your chance. Ceux qui sont présents, et vous avez le droit de quitter, mais très, très doucement. Okay? Go ahead, Christian. Welcome back, Christian. Go ahead.
Yeah, merci. Great talk, and I agree there is compelling evidence that it's pattern matching all the way down. But is human cognition also just pattern matching all the way up? In other words, is it literally just pattern matching, or are there additional structures and mechanisms involved?
The strong claim is that it's just pattern matching, but I think, it becomes increasingly hard, I think, to start drawing distinctions. For example, the distinction between memory retrieval, right, versus kind of reasoning from first principles. Like, well, okay, there are easy cases where here's an isolated fact. You've heard about the why are manholes round thing. Okay, and then you just retrieve that explanation. You don't have to think very deeply. But so there are clear cases where, okay, this is just about matching a very specific episode memory. But then, of course, a lot of real thinking is much more abstract than that. And so, like in the Jabberwocky case, it's the patterns involved are these weird structural things that depend in some cases on punctuation, and that, okay, because this is an uppercase thing, like the context in which it occurs as uppercase is different from right? So it's not about matching this very specific pattern, but these more abstract structures and aligning on these more abstract structures. And whether one calls that, pattern matching, or so I think of like Dedrick-Gentner's structural alignment, right? These are obviously more abstract data structures, but it's still about types of similarity. And so for me, that would count as a pattern, but I'm not, wedded if someone wanted to say, well, at that point, it's not really fair to call it pattern matching.
So I would agree that it's absolutely fair to call it pattern matching at whatever level of abstraction and complexity of the representation. But if I may have a quick follow-up. So Pilishin talks about algorithmic equivalence.
Yeah.
So which gets sort of beyond those questions that you were talking about, of sort of like, well, is it this or that? Do you think that human cognition is algorithmic equivalent to LLMs and transformers in general, or the way they do tasks, for example, whatever task is different?
I think there are cases where there is algorithmic equivalence at some broad strokes. I think that there are, because the implementation is so different. The energy use required by LLMs, the way that LLMs can hold these enormous context windows sort of in more like working memory, right? Those are very different from human brains. And that's going to impact the kinds of algorithms that are runnable, And so just from like one informal observation from doing this Jabberwocky text, it seems to me that if you look at the process the model undergoes during its translation, it's much more willing to revise hypotheses than people are. So people are stickier, and it's harder for people, in these kind of like, okay, just look at this and try to figure it out cases, to do like, to be good Bayesians and to like, okay, well, now that I know this, I should revisit this thing I've committed to earlier, right? And LLMs seem to be better. So is that a different algorithm, or just like, well, they're doing constraint satisfaction, but in certain respects, LLMs are more effective, and maybe other respects, people are more effective at this. So I think if you drill down, often, there's not going to be like one-to-one match.
I think that Zenon Pilishin is overreaching when he asks for strong equivalence in cognitive science. You don't even have it in physics.
Yeah.
Okay, now, next question, Douglas.
Hi. So thinking about the example you gave where you had a sports paragraph where you put in all the blanks, I'm pretty sure I would have gotten a 0 on that, and wouldn't have been able to tell you whether it was about sports or whether it was from the Wall Street Journal. So that must mean that the LLM has access in the data that it's seen to something that I don't have. But from a Shannon information point of view, you would say, oh, the amount of information in the message depends on how many possible messages there are. Well, so the LLM knows about way more possible messages than I do, so you would think it would do worse. So what am I missing here about what the LLM can pull off? Or is it just a matter that it's not Shannon information, it's searching through a search space and it's very good at doing that fast?
Yeah.
So it's certainly not a serial search through a search space, but it's constraint satisfaction, parallel constraint satisfaction. So I think you would actually do better on this kind of task than you think. So when we test this on people, for people to figure out genre information is pretty easy, right? Because, and it's almost like cheating. It's like, oh, well, there are a bunch of uppercase things that looks like a screenplay, or, there's lots of like ... that's the kind of thing I expect from a spoken language transcript. So that type of information is already cluing you into a general topic. And then, so with the sports example, one interesting thing there is you're totally right that if the model had never been trained on any sports news, I would expect it to do much, much worse. And people's ability to tell you that, like, maybe this is about sports, I'd expect that it would also be predicated on, their knowledge of sports. But what's interesting is how quickly you can converge. So if you can make an informed guess about the genre, you know that it's something about sports. Now you have a few numbers in there that is constraining that, like, okay, well, that looks like maybe the number of yards. And then in the context of sports, $12. Why would you talk about $12? Maybe it's $12 million. And now you're talking about someone's contract or salary or whatever. And that's part of the point, that it's very much dependent on content knowledge. Just like in that Reddit passage, for Netherlands to help, you need to know about Dutch food. And so that knowledge is being brought to bear on this constraint satisfaction. And so on its own, if it's just a single word or a single passage, Shannon information theory, there are more possibilities. It's less information. But now you start combining it. Now you have a whole sentence, 2 sentences, 5 sentences, and it just radically restricts the possibilities. And so, for example, that passage about cooking food, someone asked me when I gave a version of this talk recently, well, but how could it know that it's about cooking food, even if it gets the details wrong, and not assembling furniture? And the answer is that you could not, there isn't just like a single word that you can replace to make the passage shift from about being food to furniture. You'd have to change a whole lot and make it to maintain internal coherence. And that's enough information. And in cases where, you can just swap a single word, like someone's name, the models can't get this. And that's as you would expect. So the larger knowledge base allows it to bring that knowledge in to make the maximal use of constraints.
So semantic patterns. So patterns is semantic patterns. Thank you.
It's semantic. It's morphosyntactic. It's all of this is being brought to bear on this translation process.
Eddie, your turn.
So regarding pattern matching and regarding patterns that found by LLMs or humans, there's the further question of what is the categories, what are the categories and concepts and the nodes you mentioned in the mech interpretability research that are the categories that we write down the patterns, for example. And given different categorizations, different concepts, we might have different patterns. And is it something that people are checking is that the categories might be misaligned with our human categories, which might explain in some sense that LLMs are making more powerful inferences than humans do. And for example, in the AlphaFold, if it's not even LLM, it seems to have black box kind of inferences that we still don't understand after all these years. And could it be that the pattern matching LLM is employing concepts that are more joint carving in nature, but less apparent to us, so that we're just missing out things?
I think that's a possibility. We're thinking about some of those, same things. We don't know. And it speaks to the question about Paul's earlier question, I think Paul logged up, about notation systems. Can LLMs invent notation systems? I don't know, because you could imagine a situation where an LLM invents a notation system, a set of carving the world, right? That's useful to other instances of the LLM, not necessarily useful to people. I mean, that's quite possible. Or it might have discovered, certainly that would be a more beneficial situation from our perspective, better ways of compressing the world, right? And so better categories, better notations, right? That might improve our thinking. I mean, it's an empirical question, but I don't know.
Oliver Hart.
Yeah.
Hello. Thanks for this interesting talk about LLMs. I wonder from a different perspective about what we actually learn about from LLMs about like cognition in biological systems, because what you've shown, I mean, on the surface, they passed the Turing test. And so you could conclude that they kind of behave like an intelligent system, like a human system even. But then, for example, our ability, or let's say the ability of biological organisms to express cognitive flexibility, like in this exemplified in pattern matching or generalizations, we know now that this involves endogenous forgetting processes as an actual central element. And from my understanding, is that LLMs are pretty bad at that. So they're really bad at forgetting stuff. And so I wonder whether the way we achieve these kind of things is fundamentally different, because we have all these, let's say, other mechanisms in place that curate our memory, and notably, basically, forgetting processes.
Yeah. So I would not want to argue for strong equivalence. It's better to take it case by case. With regard to memory, the memory, yeah, it's quite different. I mean, on the one hand, LLMs instantiate memory in weights, as connection systems do, which is, broadly similar to people as far as we know. On the other hand, people have, there's no distinction between learning and deploying one's knowledge. So everything we experience is leaving a trace, is being learned. And in LLMs now, it's not an in-principle limitation, but as they are implemented now, right, you have context and you have its ability to use in-context learning, to make maximal use of its prior knowledge. But then there is the frozen weights from pre-training, right? And that's very different from a biological system. So in that regard, it's different. And so, they don't forget, or they, from a different perspective, they don't remember anything, because you can, new context window, right? And of course they have memories of, from prior training, but there's no continuity, there's no sense of time, which is also an interesting difference. Like, what would human cognition be like if there was no time? We have no idea. So yeah, I want to be careful, in drawing too strong a parallel.
Thanks.
Okay, Eddie.
Thanks. So as a philosopher, I want to press you on one conceptual point that I worry that maybe this is one thing where we disagree, because I feel like we do agree on many things. A lookup table, database idea, many people say it is not intelligent, it is not understanding. And I think you mentioned this early in your talk. I think in other talks you gave, I saw on YouTube, that this might be an example of a gigantic lookup table is not understanding. But what if, suppose we have a world in which laws are so more permissible, that you have a gigantic lookup table that computationally implement the same kind of, algorithm as a pattern matching system like us and like LMs. And that system, does it understand? Does it not understand? I mean, this is kind of just clarifying the concept of understanding and intelligence.
Yeah. And I know people have very different and strong opinions on this. So, to me, like one reason why people want to say that lookup tables don't understand anything is that we expect certain kinds of behavior from a lookup table that's very inflexible. It's very it doesn't generalize. It generalizes sort of in a step function. It's like, oh, now no, lookup failed, total collapse, right? And if we were to see this in a system, it would not seem very intelligent.
True.
But it might well be that this is just a limit to our imagination. And you have a large enough lookup table, and it can demonstrate all the right kinds of flexibility. So, and useful generalization. And so, if one were to discover that a system that does human-like things behaviorally, like, oh, look, we did the right analyses,
Right.
and it's just a lookup table.
Right.
I would personally be fine with saying,
right,
well, that's unexpected, that's surprising, but if I thought it understood things based on its behavior, knowing that underlying it is this lookup table wouldn't change my mind.
good.
Now, it could be that, oh, now that we know what the lookup table is, we can create situations, right, that any system we want to say understands should be able to still behave appropriately, but like now it just fails, right? And ironically, like, we can create, adversarial situations for people where it trips them up, right? We can create, questions. So normally, our confidence is pretty well calibrated. And so when you're not sure about something, you're more likely to get it wrong. But we can create questions, like trivia style questions, that have very attractive lures. And so people are very confidently wrong in those cases.
This is very helpful because I feel like this is the consistent way of thinking about functionalism, computational theory of the mind, and Dennis patterns and connectionism. But I feel like many people have this tempting intuition that a lookup table cannot possibly be intelligent or understanding. And that's the intuition I feel like is inconsistent with the paradigm thinking computationally, thinking functionally, thinking behaviorally, connectionally.
Yeah. But that's I think in the real world, pattern, like lookup tables are just not a very efficient system, so it's unlikely to be.
One second. I'm being overridden. So what I want to say is, Mylène, tu peux couper l'enregistrement en continu et puis